Welcome everyone. In this video, I will be covering section 11.1, which is about sequences. The whole of chapter 11 is about sequences and series. The very first section of chapter 11 is only sequences. All the rest of the sections, 11.2 through 11.10, are about series. What is a sequence? A sequence can be thought of as a list of numbers written in definite order. A1, A2, A3, A4, etc., AN, and so on. So A sub 1 stands for the first term, A sub 2 stands for the second term, A sub n stands for the nth term. So to give you a quick example, we have seen many examples like this 2, 4, 6, 8, and so on. They follow a pattern. The terms follow a pattern. If you look at this example, in this, the terms increase by a quantity 2. The starting term is 2. Then you can give a generic representation of the general term. If you notice that second term is 2 times 2, third term is 2 times 3, fourth term is 2 times 4. So we can give a general representation of the generic term. The sequence, which can be written in curly bracket by listing the members inside a curly bracket, is also denoted by writing the nth term inside a curly bracket, or we can also write the sequence as sequence in curly bracket A sub n, which is the nth term, n starting from 1 through infinity, n starting from 1 through infinity. So that's how you can represent a sequence. The following are some different ways of writing a sequence. You can write the nth term inside a curly bracket by giving where it starts, where it ends. So it's an infinite sequence which has infinitely many terms. Or you can just write a recursive way of writing the terms, like nth term is n over n plus 1, which means you have to give successive values for n. Then, like this, you can write down the members inside a curly bracket by listing down the members. So, how do you get that first term 1 over 2? So, here in this, if you plug in n equal to 1, you get this term n equal to 1 divided by 1 plus 1. 1 over 1 plus 1, that's how you get the first term. So A sub 1 is obtained by plugging in n equal to 1 into A sub n. So it is 1 over 1 plus 1, which is 1 half. A sub 2 is obtained by plugging n equal to 2. So it is 2 over 2 plus 1. So n over n plus 1. The n gets replaced by 2. So you get 2 over 3. Then n equal to 3 gives a 3. So you have to substitute 3 divided by 3 plus 1. So only n gets changed to the value that you plug in, which is equal to 3 divided by 4. So you get A1, A2, A3, and so on successively. And this is the nth term, generic term. So like that, if you take another example, negative 1 to the power n and plus 1 over 3 to the power n, we can write just by the nth term alone, or we can list down the members inside a curly bracket the way it is shown. So if you plug in n equal to 1 here, you should get a1. So it is negative 1 to the power 1, n plus 1, so 1 plus 1 divided by 3 to the power 1. So you're going to only plug in values for n. So it is n plus 1 here 1 and n plus 1 here 3 to the power n. So wherever n is, you're going to replace that by the value that you plug in for successive values of the terms. So it is negative 1 to the power 1, which is negative 1 times 2 divided by 3. So it is negative 2 thirds. So when you plug in n equal to 2, you should get a sub 2. So if you plug in 2, it's negative 1 square, then 2 plus 1 divided by 3 square. So you are plugging in only for n. So it's n equal to 2, n equal to 2, n equal to 2. To get negative 1 square, which is positive 1, that then you have 3 divided by 3 square, which is equal to 9. So you get the second term. So you get successive terms like this, a sub 1, a sub 2, a sub 3, like that. So if you want to start any sequence with a negative sign, and you may want to attach negative 1 to the power n. This negative 1 to the power n pretty much alternates, alternates the signs of the terms starting with the negative. If you want to start this sequence with positive sign and then alternate sign, positive, negative, then you may have to introduce negative 1 to the power n minus 1. Then the sign will start off positively. Find a formula for the general term an of the sequence. So we are going to find out, we are going to look at the terms and come up with a generic expression for this. So if you look at the first terms alone, the first term numerator starts with 3. The very first term start with 3. The second term is 4. Looking at only the numerical value in 3, 4, 5, 6, 7, and so on. So the first term doesn't start with 1. It starts with 1 plus 2, 3. So the second term numerator is 2 plus 2. Third term is 3 plus 2. So the position of the term plus 2 is the numerator. So then if I have to write down the nth term, then if I look at only the numerical value of the um, numerators, it's the position of the term plus 2. The first term is 3, so 1 plus 2. Second term is 4, so it is 2 plus 2. So that is the numerator. If you look at the denominator, it's all exponents of 5. The first term has a denominator 5 to the power 1. Second term has a denominator 5 square. Third term has a denominator 5 cube. So nth term must have 5 to the power n. And also you notice the terms are alternatively positive and negative. Because it starts off positively, you have to attach negative 1 to the power n minus 1. Because when you plug in a 1, n equal to 1, you get the first term, so which is negative 1 to the power 1 minus 1, which is 0, then 1 plus 2 divided by 5 to the power 1. So, so where do we plug in? N equal to n here, n minus 1 becomes 0. So you get positive 3 over 5. That's exactly the first term. So similarly, you can check the rest of the terms by plugging in successive values for n starting from 1. So this is the nth term in this problem, the generic term. A sequence in example 1 um, with nth term an equal to n over n plus 1, this particular example here, can be pictured either by figure 1 or by figure 2 below. So you can either, so the nth term is n over n plus 1. So if you look at this example, the first term is 1/2, second term is 2/3. The first term is 0.5, second term is 0.6, 6, the third term is 0.75. It slowly increases to the value 1, right? So if you look at this figure, so A1 is 1/2, and then A2 is 2 over 3, and so on. So you can plot the terms of the sequence as shown in this picture, or you can also plot the points as shown in this diagram, the second diagram. So for the first term, A1 corresponds to 1/2, then 2, and n equal to 2, A2 corresponds to slightly more than half, 0.6, 3 corresponds to 0.75, and so on. So seventh term corresponds to 7 over 8. Then it goes on and then it reaches, it approaches the value 1. So the way we say that is limit is n approaching infinity, n over n plus 1 equal to 1. So we can see that pictorially. Also, from your maths calculus 1 class, the limit n approaching infinity, n over n plus 1, it's kind of finding, you used this technique when you did horizontal asymptote or limit problems. So divide the numerator and the denominator by the highest exponent of the denominator, which is by n. You still need to apply limit as n approaching infinity. So you divide by n. So it is limit as n approaching infinity, 1 numerator, divided by n plus 1 over n, so which is n over n plus 1 over n. And we know that 1 over a large number is 0. So numerator is 1 plus n over n, which is 1, plus 0, which is equal to 1. So you can prove that way too. The limit as n approaching infinity, n over n plus 1 equal to 1. You see that in the picture shown in figure 1 and figure 2. What do you mean by a sequence having a limit? The sequence an has a limit L, and we write limit as n approaching infinity, an equal to L, or we say an approaches n as n approaches infinity. What is a convergent sequence? A convergent sequence an is an ordered list of numbers when limit as n approaching infinity an exists. If the limit does not exist, it's said to be divergent. So if you look at the two sequences that we have in these two pictures, in these two diagrams, in these two graphs, you notice that the terms goes in this way, then finally, eventually it approaches the value L. Okay, it can go increase and decrease, but finally, in the long run, it approaches the value L. Same way, it goes in the second picture, it goes like this, it goes down, it goes up, but eventually it approaches, it comes very close to this L eventually. So it is, these two are examples of limit, the sequence approaching the limit L.